treatment they would provide was related to their ability to figure out what kind of anesthesia I've received recently, recent surgical experiences, what kind of drugs I might be in my system. So again, their ability to do their job and get me out of the country alive was directly related to their ability to share data that was fairly private in nature. So okay, that was slightly fictitious, but I have been to the UK. All throughout this, data are stored. My health record, my exams, but even more mundane things like my pictures and my daughter's pictures and emails I've exchanged with people are stored on my machine, on my friends' machines, on the cloud, and oftentimes interesting things happen to those data objects. So, for example, I've been subscribing to 23andMe, which is a company that does DNA analysis, and they tell me when I'm going to die and interesting things like that. They have a lot of very intimate information about me. Also, while Google Health was still healthy, it used to know about my medical record and tell me about weird drug interactions or new identified patterns that I should be worried about. Again, very deep information that they had available in their servers. And of course, I'm not part of this, but there's all these interesting, morbidly curious people who want to exchange MRIs and EEGs and all sorts of tests, somewhat for research, but also for other purposes. And those kinds of communities exist. All in all, the interesting thing is that there's a lot of data that we can't just shove into a vault and keep held and isolated from the rest of the world forever. In some cases, critical, important data has to be shared, and it has to be shared fairly intimately and intrusively. It has to be modified, it has to be annotated, it has to be looked at, it has to be perhaps changed and extended in interesting ways. And yet, these are the kinds of data that we don't necessarily want to make blanket public declarations about or make available to anyone to modify in any way they want. We have some restrictions on how they're used. The problem is once you disclose your data as things are right now, the horse has left the barn. That was the set operator there, the horse not in the barn at the bottom of the slide. So once that happens, basically your only choice is to either allow anyone to do anything undetected or die, at least in the case of health records. That might be overly dramatic. So, okay, that's what we can do, but is that justified? Should we be really worried about this stuff? Well, we should, because companies that claim they do no evil do still have cases where their employees look at data they shouldn't be looking at, and promptly employees get terminated as a result. There's social companies out there that have very complex privacy policies that real people without PhDs in security can't really fathom, and actually even people with PhDs for that matter. So they make the wrong decisions and sensitive stuff ends up being disclosed to everyone. There's this very interesting case, this second on the left column, where this man in Orange County was hacking into people's computers, finding naughty pictures of the computer owners in there, and blackmailing people, not for money, but for more pictures that he turned around and sold. So there are all these kind of interesting, creative ways that enterprising spirit finds to use sensitive data in ways that were unintended. And of course, the mom and apple pie kinds of cases, like Aurora, which broke into Google and Intel, I might add, and violated all sorts of perimeter kinds of protections, looking at data that shouldn't be looked at. The PlayStation breach, Netflix, the anonymization of data, and all sorts of things like that. So things are kind of dangerous for your data out there, whether they lie in your desktop or in your friend's desktop or in the cloud. And one approach is to curl up into a ball and hide from the world and go off the grid. But that's not a very productive way to live your life, and in most cases, not a very good way to get a PhD thesis out of it. So instead, what we would like is to have the data bodyguard, someone who's strong and well-dressed in this particular case, who will sit down there, you give them your data, and you say, this is my policy, this is my data use controls kind of declaration. We call them DUCs because it sounds good to have data with DUCs. So here's my data, and here's my data use controls. Please enforce them. Do the intelligent thing when someone, some web service, some friend who has a need to modify or look at my data, enforce my intent and the letter of my policy, and thank you very much. Problem is, super friends like that are kind of expensive. They have, the suit and the tie that's expensive, but also you need to provision them. They have to be available, and frankly, you pay the trustworthiness that you want. You can't expect them to be trustworthy if you don't really pay them enough to invest in the policies and technology that makes them trustworthy. So all of this is trying to convince you, and hopefully I've somewhat succeeded, that we need someone who's going to take good care of our data when the data are out of our control. The question is, how do we do it without the suited guy? And I'm going to talk about 3 choices. These are 3 of many, many points in the very complex design space that we have followed. Nothing says that these are the best 3 choices, but they're the 3 choices that we've explored so far. The interesting thing is, well, there's many more in between them that hopefully some of you here and others will explore. We are definitely planning to. So on one hand, there's one project I'm going to talk to you about, which is called Secure Data Preservers. And there the idea is, well, treat data in the good old abstract data type kind of way, and the object-oriented way, where they have a well-defined set of operations. And you're going to do your, the hardest job you can to ensure that only the interface, this declared set of operations, are ways in which the data are modified or looked at. Assume that that's a good interface, and then ensure that all web applications, everything that looks at your pictures on Facebook or your health data, goes through that interface to access your data. So this is more of a refactoring kind of approach. Then I'm going to tell you a little bit about the secure data capsules work, which is taking a more militant approach. It says legacy is key. We can't expect anyone to change applications out there because there's so many of them, and if you expect them to change, nobody will adopt this solution. So there it says, make legacy the first priority and figure out how invasive and how crazy you have to get to make existing applications work while still enforcing data use controls on data. And then I'm going to give you a little bit of a compromise. The last couple of slides will be about this platform for private data that we're working on currently that tries to make a compromise by taking away some of the broad applicability of a solution in favor of better assumptions and stronger results, stronger guarantees. And with that, let me start by telling you a little bit about data preservers. With data preservers, I should say, if you have questions, you don't have to wait until the end. Feel free to interrupt me, and I'll ignore you if I have to. So with secure data preservers, the API is the boundary. The main approach here is that if we have particular kinds of data with a well-established interface, let's say images, audio, structured records like my web logs or my key clicks or my preferences when I'm watching stuff on Netflix or elsewhere, I can protect this well-defined interface around my data and express my access control demands, my policy, in terms of those operations. Who can look at my image, who can enlarge it, who can crop it, who can do things like that. So in the medical imaging story that I was telling you before, you could imagine a scenario where there's a view operation, a crop operation, a resize operation, or an attach text note operation, in which I would like to go, I or someone who knows better than me, someone who, for example, generates policies for people who are not sophisticated, can say, well, the radiologist can view, crop, or attach text notes on the MRI scan, but the treating physician can view and resize. This could be arbitrary in practice. So with this kind of approach, the story we take is, well, take an existing web service where right now you have the service code, the service data, and my user data interspersed and splattered all over the address space of the web service. And I transform it into this sort of partition view in which now my data and the code that's supposed to implement the interface, the well-defined interface, live on one side of an isolation barrier, and the service, untrusted service, as far as I'm concerned, lives on the other side of the isolation barrier. And only stuff that follows the well-defined interface crosses the isolation barrier after my policy has been enforced. That's the sort of logical view of what it is we're trying to do here. So what kinds of applications are suitable to this type of partitioning? Not all of them are. We have identified some idioms that sort of are well suited to it from the kinds of web services that are available out there today. One kind of idiom we call the sensitive query, in which a user provides something, some kind of a search string, a search query, which is itself the sensitive data, and it's supposed to be applied to a vast set of data that aren't necessarily sensitive. So think of the case where you do day trading. People who do day trading do some really interesting things with saying, you know, when the first derivative of this stock ticker and the second derivative cross over and the moon is halfway through, then go buy, sell, or both. So this, in a sense, is strategy. It's something that's fairly dear to paranoid people who do this sort of thing. I'm not very good at the stock market, so maybe I should know better. So in this case, that's the sensitive secret sauce of what my data living on a brokerage firm's web service is. The stock ticker itself, well, okay, I pay for it, but it's not a secret. So in a sense, you could put quotes around it. The idea is preserve the query, but push the data through it. The sort of flip version of this is analytics on sensitive data, where the data themselves are sort of in a more traditional sense, the sensitive stuff, and queries are applied by the service on my behalf. So things like my web clicks or my preferences of what movies I like to watch or what music I like to listen to would be the sensitive, personally identifying information there, and I want to run interesting, cool queries on them to tell me what I should listen to next or what I should buy. So here the idea is preserve the data and run queries through them. And there's sort of a half idiom last that sort of looks at proxying. You take the credentials, like my credit card number and my verification code, you bundle them into a little bit of a preserver, and then you give a service like Amazon the ability to say charge $10 to this opaque credit card. In some sense, lots of credit card companies already do that sort of thing, but you could sort of imagine more complex cases where this proxying of sensitive data can be done. So here, preserving a secret and running access requests through it is the third idiom. Yes?
So what does it mean preserve? So if you pick one example, second example, what does it mean preserve the data? What is it that the service is not getting?
So obviously it depends on what actual benefit you get out of the service. But so you're talking about the second idiom, correct? So here you could imagine a situation in which the service says, I'm going to target some advertising to you, and I'm going to pick one out of, let's say, 10 ads that might best suit your viewing behavior so far. So I can essentially run the query, which is looking at, I don't know, keywords, whatever it is that I have done so far in a closed box, and then returns to me directly the answer of, well, watch that ad. Obviously, if you're trying to do, for example, recommendation engines across multiple users, that wouldn't necessarily work. But there are cases where extracting the logic of targeted advertising in a sort of in an algorithmic sense, where you categorize keywords and then you classify a particular user's history within basically a decision tree, works reasonably well. You can be arbitrarily expansive with this kind of approach. So for example, for large-scale analytics of multiple users or entire user populations, this might not quite work. So that was the idea here.
So I guess a more detailed question is, what is the privacy guarantee?
Well, the privacy guarantee is that somehow I've convinced myself.
Maybe move that away.
No, it's anybody in the room. you say with your keys in front of your microphone, we will hear it. So just, if you want to do that, then that's what we'll hear. Yeah, thank you very much, Mark.
Now we know.
So it's not you. It's just your lovely audience.
I'm used to being me. So the approach we're taking here is one in which the API is sacrosanct. I know that the API, whatever it is what I need to enforce and what I need to provide access controls on, even if it's a stupid API. And you could have a stupid API. We're actually going to talk about this right next, in which you say, okay, it's an image, and I explicitly forbid anyone from cropping the image, but I also provide in the API a raw read and write bytes into the backend store. So if you can express an operation in terms of other operations, if the API is not minimal, then policy might not make sense. So for now, we're sort of hiding. We voluntarily say, well, I don't care what the API is. I want to just enforce it. Finding a good API is actually a very interesting question. So this would be the API here, one in which, well, give me a stream of watched stuff or seen stuff or listened to stuff, and I'm going to pick one of these 10 given ads for you and tell you in a secure fashion. I don't know how much privacy it gives. All it gives is isolation on the API. So interestingly enough, so how are we doing with time? 26. I was going to tell you that, oh, there was another question?
There's a clock.
Oh, there's a clock, yes. I was going to tell you that what's a good and what's a bad API might have to do with semantic well-fittedness, like as I just described, but also might be if you have an API that's very, very fine-grained, where you have access to a gigantic set of sensitive data, one character at a time, going through an isolation barrier, depending on how you've deployed this approach, could be very expensive, so it might be a bad application to do as well. So I was going to tell you a little bit about deployment scenarios, but I don't think I will, because I don't have enough time. The main idea is you can deploy these preservers near the web service or far from the web service, and the choice of where to deploy them at a third party, trusted third party, or on my client browser, or through virtualization on the same machine as the web service is deployed over, has impact on bandwidth and latency, but also isolation. What kinds of threats, what kinds of threat models I can withstand. And I was going to explain all of this to you, but all I'm going to show you is a Kvyat diagram because it's so cool. So a Kvyat diagram is this polar kind of set of axes. There are 5 axes here that put on one side the isolation, affordability, timeliness, which is sort of the inverse of latency, throughput, which sort of says is the inverse of how bandwidth hungry a particular deployment scenario is, and availability, which says, you know, how frequently you can reach it or not reach it. And it says that depending on what weights you put on any one of these axes, the choice of the right deployment, whether you put the preserver in a trusted third party or through virtualization on the same set of machines where the web service runs, or on a secure coprocessor for that matter, might be completely different. So a fundamental requirement for this project that we started out with was, let's talk about the concept, the abstraction, the isolation, and let's leave the choice of how to deploy it until later.
Back to that.
Yes.
What's impressive to me is how near Cotenon and before are quite similar, except in the isolation. And isolation seems to be the one that's nonlinear with everything else. That's all.
Precisely. So, I mean, for everything that's near the web service, you would expect that, well, they're close to each other, so they have differences mostly because you might have to put some access controls on a function call or VM to VM, the process communication kind of thing. But the difference is that before, what we had was the web service and the data, and there was no barrier between the two. And by sort of pushing down a little bit on the capacity, the throughput of the system, because now you might have to go across VMs, or you might have to go across co-located machines on the same LAN, you get better isolation. So that's a good observation.
I'm just reading your graph.
It's but isn't it? Aren't Kvyat diagrams cool? They're great. They don't always read like anything, and especially when the green looks like the yellow, they don't mean much, but believe me, they're cool. So just to move forward with this, the whole point of this is that flexible deployment is important. You shouldn't have to compromise on the security or the privacy or the correctness that you get out of the system, depending on flexibility of deployment. And I'm going to talk a little bit about trust but mitigate risk a little bit later. I'll explain what that is. So after everything I've told you so far, this architecture diagram shouldn't necessarily be particularly surprising to you. The whole idea is that there's a separate virtual machine that could be running far away, unvirtualized, or nearby over the same sort of virtualization layer that allows you to put your sensitive data, the code that implements the data interface, a policy engine where you say, use this access method but not that, or use this one 5 times but not that, and then some hosting facilities. And there's 3 kinds of operations that can happen with these kinds of preservers. One is installation. I decide that I want to push my, let's say, my credit card payment preserver onto Amazon. I give it a bundle that is going to install in this isolated thing, and now Amazon can charge me. There's invocation, so the charging part. Amazon can go and invoke the access operations of the preserver. And there's transformation, which I'm going to tell you a little bit about later, which allows you to move preservers around and perhaps in the process mitigate the risk of having the trust you've placed on them be violated. Let's talk a little bit about hosting. So with hosting, with installation, the kinds of policy that someone wants to worry about is, well, who should be allowed to hold my preserver? We use a declarative language that looks like this secpal thing that came out of MSR, but any kind of declarative language or any kind of policy language would work. Policy languages are themselves kind of a very hairy problem that we haven't solved. All I'm going to tell you here is that the kinds of things that you should be able to express is, well, Alice is the owner of the data here. She can say that, well, a machine can host my, let's say, my charging preserver if that machine is owned by Amazon. It's basically a horn clause. It's a logical statement that says if all the things on the right-hand side work, then the left-hand side is true. Or it can be something more interesting that says, well, anyone can host my my payment preserver as long as they're a trusted service for some definition of trusted that I'll tell you next. And the service owns the machine, and the machine has a secure coprocessor like the IBM 4756 or 64, the latest one. And of course, Alice or someone may delegate the definition of what a trusted service is. Now, my mom doesn't do very well with horn clauses, so I can't imagine her to write this policy for herself, but you could imagine situations where policies are written into templates that I can point and click and specify. It is a hard problem that I'm going to tell you a little bit more about later. A slight variation of this is invocation. So who can actually invoke the operations in my preserver? It's kind of interesting because now you may have cases where your policy might be stateful. So you might want to say you can only invoke, let's say, the charging interface 5 times. So there could be things like limitations of how much money you want to charge for, or let's say how much of my web accesses, what percentage of my web accesses over the last year you're allowed to munge and analyze for targeted advertising. Or things like temporal limitations on when operations can be applied, or even things like delegation. An example for delegation is, if you imagine Amazon. Amazon is a complex service that actually employs other services as well. Let's say Audible, which is a service that Amazon bought that does audiobooks. It would be nice if I could say, well, Amazon can charge my account up to $50, but I want to buy an audiobook. So Amazon might have to push my preserver to Audible to spend some of those $50. Well, somehow you have to keep consistent what has been spent by Amazon itself and all its delegates. So these are the kinds of stateful, distributed kinds of questions you might have to deal with. So transformation is also related to this. Here the idea is, well, yes, we trust that the machinery that we have created will protect access to my data. But what happens if my trust has been misplaced and the data is disclosed in the raw? So there are two kinds of things that we do to either contract or expand the amount of risk we're willing to take on with a particular preserver that lives at a particular place. In terms of contracting, in the example that I gave you about Amazon and Audible, one might say, well, Amazon has all my purchasing history for the last year, but when I want to ask Audible for some new audiobook to listen to, Amazon doesn't have to give them my entire preserver with all the underwear I've bought and all the movies I've watched and every, I don't know, gift card I've given to my friends. They can just filter out and only give them books. So this is an instance where the interface is there. The interface, if I trust it, tells me that Audible will only be able to access the stuff that I give them leave to access, but they will have the data. It will be on their infrastructure. If trust is violated, this allows me to mitigate the risk that I'm exposing myself to. Sort of the opposite of this is aggregation. Let's say we were talking a little bit earlier about recommendation engines that involve multiple parties being better than recommendation engines that involve only my watching habits. If I have a bunch of friends that I'm not particularly paranoid about and I'm willing to tell them what I've watched, they're willing to tell me what they've watched, I can merge preservers. I can merge my watching habits and their watching habits and get better recommendations of what we together think the next thing I should be watching would be. So aggregation, in a sense, is exposing myself to more risk because I'm willing to tell my friends exactly what my sensitive data looks like and let the service pretend that we're all one happy family. So we tried this thing with a bunch of different deployment options, and we tried a day trading application, some targeted advertising that's meant to allow me to protect myself from for having my watching habits exposed, and an open source shopping cart that we were trying to bundle up and proxy. And we looked at lots of things like the traditional systemsy kinds of things to worry about, the cost of invoking and the cost of transforming and installing. And we started trying to write a formal analysis for it, but it's not quite done yet. It was an exercise in trying to figure out, well, if you believe in these interfaces, can you isolate them? And does this buy you anything? And the answer was sort of a qualified yes. The qualification comes from the fact that who knows what a good interface is? Who knows if the privacy of the data that's sitting inside the chewy middle of a preserver can be reverse engineered by looking at the sequence of operations and their responses as the preserver is running. This is information that you have to get about the semantic fitness of a particular interface, a particular preserver, that just isolating on the interface is not going to give you. But the interesting thing about it is that there are all these standards organizations that say that this is what images should be handled as. And in those cases, when the interface is there, it's by de facto an interface that's universally adopted. Something like this might work for. Okay, so this is a systems talk, so there's some numbers. Let me talk about the next project. So the next project, the Secure Data Capsules project, came out of our concern that, well, who knows what the right interface is? And at the same time, what? I need to refactor my application? That's crazy talk. So the way we started, the mindset we started with here was, let's say that we don't have to worry about the semantic connotations of a particular interface. Let's say that we use something that's very easy to understand, which is bits in, bits out. Let's say that my sensitive data is just a bit bucket, and I want to protect information flowing in and out of my sensitive data. My data use controls as expressed as they were before in terms of information flowing in and information flowing out. Provenance is nice, so it would be nice to know how my sensitive blob of data, of bits, has changed as it's moving from machine to machine and from service to service. And if I want to add application-specific policy on top of that, things that talk about cropping and resizing of images in the examples I've given you, hey, that's nice, but still the raw data level restrictions should still be adhered to. So our goal here was to support current operating systems and applications without limiting choice in terms of pre-partitioning or adopting a research operating system that does funny multi-level security kinds of solutions, or there's a whole slew of research work that has come out on decentralized information flow control that allows you to keep track of very fine-grained or coarser-grained levels of information as it's moving from component to component in a large system. It has to be Windows, it has to be Linux, it has to be something that exists and is being deployed right now. But even though it exists and it's being deployed, we want to remove it from the trusted computing base. And what we leave in the trusted computing base, we want to argue that it's small enough, or we want to actually do the verification part on it. And we want to provide acceptable performance. You'll notice the performance is the third priority, so we're willing to take large compromises on performance. However, legacy is the killer app here. We said, okay, it's nice to go and refactor things into preservers and non-preservers, but let's talk about something that will work with existing applications. So the architecture that we derived was very similar to what I have described so far, with some differences. Now, we don't have the benefit of partitioning. We don't have the benefit of a well-ordered separation between the sensitive stuff and the insensitive stuff. So what do? We have an unmodified OS that we don't trust, an application that we have no idea about, and some hardware. And we want to figure out how this yellow blob there, which is my sensitive information, can be used by the application. So the first thing we need to do is take the operating system out of the TCB, out of the trusted computing base. And to do that, one way to do it, there are others, but one fairly reasonable way to do it is to use a hardware root of trust, something like a TPM or some other trusted execution hardware facility underneath, and something like a hypervisor that at least will enforce isolation between the untrusted operating system and the application that has to have access to my data. So that red blob there is more complicated in practice, more lines of code, but it's supposed to separate the application from the operating system. And then once you have that, you can't just isolate them and let the application reign free, because ultimately the application must be able to expose data out, push data out into the network, and bring data in. So you need some sort of a secure execution environment that monitors the application at runtime and figures out what it's doing at some granularity. For example, system call granularity. And since all you can go by is information flowing, you need some sort of notion of tracking information through the application's address space. And of course, since the data, once they leave the containment of the application, can be seen by anyone, you have to protect them. So again, the notion of encapsulation comes up where you have the data, you have a data use control on the data, and provenance. It's cryptographically protected when outside the system, but there's something that understands policy, enforces policy, and authenticates particular users. So it's sort of a straightforward approach, and now the world is the same as before, except now when I'm having my MRI taken, there's a particular explicit policy that's being assigned to the imaging scan that comes out, and some provenance that say that the particular nurse took it. And then when someone has a need to modify, not only provenance is maintained, but also the policy is evaluated. And whatever application he's using, it could be Adobe Acrobat, or it could be, I don't know, Microsoft Paint for all that matters. Whatever application they want to use, they can use to annotate what they need to annotate. And the way that works is, well, let's say Dr. Magneto here wants to look at my MRI scan, and the MRI that came out of the machine comes in, is protected by a capsule. So now he knows that, or his machine realizes that it has to use something like late launch or some way to do a trusted boot of a part of this application that runs the secure execution environment around the application. So that's where the hardware root of trust comes into the picture. And now, when the capsule comes in, the particular necessary encryption keys have to be released to the engine that comes out of the authentication machinery. And then, if the policy allows Dr. Magneto to read my stuff, the capsule moves in and is decapsulated in the process. And now it's in the clear. The application doesn't even know it's running inside this container. And now, of course, because all we can go with is an application that we don't know before, we don't know anything about what it's supposed to do, we have to track the information through it. So it's fairly standard how we annotate the memory that my MRI has spread over when I first give it to the application, track how that information propagates through the system. And then on the way out, if it's dependent on my sensitive data, then the policy engine can say, okay, that can be disclosed, but it has to be properly encapsulated into a new capsule with the extended provenance, possibly a combination of policies from all the inputs, possibly an X-ray that was taken with different kinds of characteristics on the way in. If it's an unrelated piece of information, then it can just go out unfettered. So that's all very nice and good. There's a reason this is a research project. And the reason is that flow tracking, information flow tracking does a lot of the heavy lifting, and it does it very, very slowly. I don't know if you have looked at the literature in that space. Information flow tracking essentially emulates every single instruction executed by the processor and says, okay, the input to this addition is tainted, so the output should be tainted as well. So very, very expensive kind of monitoring of what's going on in the system. Naturally, it's slow. So there's lots of tricks that one has to play to make it less slow. Some are, well, not all instructions that you're executing need to be monitored. So finding some statically what needs to be monitored is important. And there are things like coarsening the granularity or deciding until later whether something is tainted or not, and so on. I talked already about verification and the difficulty of coming up with good, meaningful policies for privacy. And there's, of course, some really hard problems, like the fact that depending on how you send packages out of a contained application, even if they're protected by cryptography, even the timing in which they come out might give information if the application is malicious. So these are called covert channels in general, and they can be very tricky to contain. It's a little easier to deal with them when you have an application that you're containing versus an entire operating system, but still, this is a hard problem. So we've done some of it, and we're working on it a little bit more. The interesting thing here is, yes, we don't have to worry about interfaces. The semantic interaction between the privacy system and the application becomes very, very simple. It just flows of bits in and out. But now we have this really invasive emulation of all instructions that's going on, which, you know, maybe Intel someday will sell processors by doing it in hardware, but until then, it's going to take a while, and you're going to take a huge hit in the performance of the application. So is there something in between? I don't have much information on this in-between thing. It's something that we're working on. But the idea here is, well, maybe we don't need to solve all the world's problems at this particular point in time. Maybe it would be possible to restrict the scope of a solution and in the process get a simpler solution for the whole thing. So the idea that we noticed here was that in almost all cases, even long-running web applications don't really mix information very much. If I'm sharing a document with someone on Google Docs, often the instance of Google Docs that's running on my browser and at the server at one time only handles information that I and that other person I'm sharing with are already sharing. So I don't really have to worry about tracking information that might be coming from arbitrary other people out there in that particular one instance of the application. At the same time, for pieces of a web application that do a lot of sharing, that usually happens at the back end. There will be a common backing store that does key value storage, or there might be a database that's used by all the instances. But those are not kinds of pieces that change the semantics of the application. I don't see the fact that the application is running a database in the back end as something that changes the features that the application offers to me other than performance. So the key idea here is, for those applications that don't do much information mixing in the front end, it might make sense to perhaps more easily split them into the front end and the back end. The front end is what adds features, and You can contain it and keep track of information flowing through it, but you can do it at a coarser granularity than with what I described before with the capsules. And for the back end, you just isolate it, let it do its thing, and then on the way of information back in, you just ensure that it's only information that should be seen by the front end. I didn't give you much information. It sort of looks like this, which may not mean much to you, but the idea is take an existing application, split it into the stuff that affects the features from the stuff that affects performance, put an isolation barrier in between the two, and then you don't have to trust the trustworthiness of the application developers. They can write whatever they want, and you don't have to go and figure out specifically what policy to enforce so that the application doesn't leak users' data. And at the same time, the platform provider, the Googles and the Rackspaces of the world, they don't have to worry about the applications they're hosting compromising the privacy of the data of their users. So this is work in progress. It's still going on, and if we ever finish it, I'll tell you more about it. Until then, and since I'm running out of time, I'm just going to close with 2 more slides. So this is just scratching at the surface. Lots of people want to solve this problem. Mozilla wants to solve it. Google wants to solve it. Everybody wants to solve this problem. And they want to solve this problem because people want to move their data into the cloud, and they don't want to because it's insecure, and they don't know if they're going to retain any kind of control over the data that users or services or organizations have. Part of the problem is that many of the solutions that exist are sort of faith-based. We say, well, there's a hypervisor that's going to enforce isolation, but how good is that hypervisor? We measure how good a hypervisor is by how small it is. And that has some connection to, getting a hard-earned mathematical proof that it's correct, but until you actually write the proof, you don't really know. Not to mention that small code tends to be small not only because it has to be trustworthy, but also because it has to be fast. And unfortunately, the kinds of things that make code fast are the things that you can't really write theorems about. There's function pointers, and there's weird loops, and there's self-modifying code. All of these things exist in how operating systems work and how hypervisors work. So figuring out how to remove the faith out of the picture and get math into the picture that will tell you that a particular layer that enforces isolation, regardless of the model of sharing and protection, is hard work. And I think it's a great space to work in. Legacy won't go away. The applications that are out there are much more and greater and more popular than any new application that we'll come up with in a new type-safe language or in a language that's statically typed and all these nice things. So figuring out how to deal with legacy systems so that we can get good understanding of their privacy guarantees is important. And even figuring out how to automatically slightly modify legacy applications so that they're more analyzable dynamically or statically is going to be hard. And I think there's directions people are taking, but it's still a hard problem. Unfortunately, humans won't go away either. And somehow we need to make sense to humans. They can probably write a privacy policy that's in a high order language, but my mom doesn't speak high order logic very much, and I don't think she wants to learn. So figuring out what a privacy policy means, understanding the effect of a privacy policy on the data in a sort of what-if kind of scenario, understanding how to aggregate intuition into something that's visually compelling to a non-sophisticated user is important. That applies to application developers as well. Application developers are not security experts. Security experts often don't know how to set these policies. So this is a hard problem, and we have to figure out how to help with it. And also we have to help, I think, the business people figure out how to sell privacy as an important concern. Intel, I work for Intel. We love security because it allows us to put bullets into PR materials. But until we know exactly how much we can sell it for, it's very difficult to justify putting in billions into gigantic center that researches formal verification. So sort of doing the socialization aspect of security and verification is kind of important as well for privacy. And with that, I'll close by saying you can help. You can help because much of this research is going on in an open kind of environment where I'm part of this Intel Science and Technology Center at Berkeley that works precisely on security and privacy for the benefit of the common users out there, the non-sophisticated users. We're working on things like isolation, boundaries, and data privacy, but also on things like mobility and analytics as well. We have a lot of problems, not enough time. Would love to work with you. If you're interested, if you want to have a project on this, the benefit of working in academia for me, coming from industry, is that I don't have to worry about intellectual property restrictions. So if you want to work with us, please talk to me or click this on the projection screen over there. And with that, I will stop.
At this point, we ask some questions, and then we'll move out into the hall in about 10 minutes to have more personal conversations. Tony?
Hi. So when you talked about abstract data types, it reminded me of all these capability-based systems and the issues that arise there, because you can, in fact, have a capability-based system, which this has some elements of, which passes capabilities to others and creates new processes, which can, in fact, be banned processes. Is that kind of within the scope of your work, or have you addressed that somehow that I missed?
No, so certainly the authority to the bearer kind of flavor of what preservers are talking about is very similar with capability-based systems. I think what we're working here with is a lot coarser and perhaps a lot less easier to push back and forth than capabilities were supposed to be in the first place. Also, a lot of the way that web services are developed today is by definition not meant to work with capability systems, precisely because things are copied around anyway, so anybody who would get the capability would get access to anything they wanted. So a lot of the stuff that I didn't talk about is which parts of the web service that you haven't factored into the preserver side are eligible to access, for example, the preserver. So there's an authentication. There is authentication. It's not just all capability, pass it around and get access here.
And then the problem with the web services is you're sending these SOAP messages around with the equivalent, and as you suggested, that just the timing of them or their content can, in fact, divulge.
Well, for preservers, that is the least of our problems, right? With preservers, the interface is what you put all your faith in. But even for the capsules, which don't really have code in them, they just have data, covert channels are going to be hard. I think the nice thing about having fine-grained encapsulation is that you can actually make the interface arbitrarily limited and arbitrarily constrained. You can constrain in terms of time, you can constrain in terms of what it can do and the order in which it can output messages. So there's lots of tricks that people have played with defeating storage or timing covert channels. Mostly it has to do with instilling either unpredictability or a canonical order in which things happen. Usually that means performance loss. But hey, the story is here. Let's get the guarantees. And so if it makes Amazon load, 2 seconds longer, I don't know. If I'm going there to buy porn, I might be willing to wait for 2 seconds to ensure that my boss doesn't find out about it. If it's my health record,
Thank you.
Sure. You're looking at me very, very suspiciously.
Oh, yeah. I mean, if I'm really paranoid, I just back things up on my local file. I don't use the cloud. If I'm using, if I'm out there, yes, my health records, the fact that I've got HIV and every other possible problem, will affect my future if the wrong people get that data. And it's like we were talking about lunch. I mean, no one values privacy until it destroys their life. So, I don't know. The 2 seconds I'm very depressed by, because basically everybody's taking 2 seconds. I mean, in the end, I've got a multi-gigahertz processor here, and it takes longer to boot up than my list machine when I was all by myself on it. So I don't know if I'm very excited about that.
I'm very excited about
my performance.
I'm very excited about the 2 seconds because it gives my company the opportunity to sell you something faster in a few years. So perhaps a slightly less glib answer would be,
so we can't trust Intel to help us, is what you're saying.
you can trust Intel to sell you something in a couple of years that will help you. So I think the slightly less glib answer is a lot of what we're doing, we're trying to separate the concept from the implementation of. For a lot of the stuff that I talked about, including information flow tracking or protection from timing from side channels or covert channels, there are solutions that we sort of know how to implement in hardware and to make them faster. They just cost wires, and they cost area, and they cost power. So far, nobody has hurt enough to give Intel and AMD and Qualcomm enough money to tell them, I want the hardware that will protect from timing channels. But when they decide that they want it, Intel will be very happy to provide it. So part of our job is to figure out, okay, what primitives would we need to have in the hardware to make all of this stuff faster? And that makes my work relevant to Intel, so I'm very happy about it.
I think it makes it relevant to the future. I mean, it's very exciting.
Yeah.
I have a question. Do you have in mind different adversary models or specific adversary models? Or because when I think of these things, I think of some specific adversary, some property, and some system, and I try to think of how these things working together to get that property. I didn't see adversary models throughout.
You didn't. So the papers talk about the particular threat models that we're thinking about. I think the kind of approach that we're going with is one in which, at least for the capsule story, there's the sort of the cloud model versus the peer-to-peer model. In the cloud model, the thought is we want to, for example, forestall insider attacks, but not insider attacks with physical access, since existing hardware will not allow us to do that anyway, but if we wanted to. And certainly we want to forestall all kinds of remote attacks, insider or outside. So certainly we assume arbitrary control of network time, message timing, and availability, so shutting down communication and so on. For the peer-to-peer kind of model, we have a weaker threat model because basically if I give you my pictures, you have full control of your machine, and part of our system model is that you have arbitrary choice of the application that you're going to use to modify my data. So you end up with a lot more power in this way because you're an insider with physical access, which makes it a little more complicated. So far, for anything but physical access adversaries, we assume full malice, but for physical access, we assume in the worst case, honest but curious.
So do you allow the programs that you've written to have bugs in them, or
Yes.
So you could have one of these applications operating on a capsule, which could have code injected into it, which could then circumvent the tracking, right? The data tracking?
The data tracking is done dynamically, not statically, so it cannot be circumvented in that way.
So there's a monitor of some sort, right? Or an emulator or something.
So you're saying code injected into the emulator.
I'm just wondering, where does the threshold for the adversary, what is their specific interface in this case?
So the adversary in this case has arbitrary access to the code of the application. The application itself can be adversarial, which means that its data, everything is within its reach. The private data of the secure execution environment, so the thing that might be a dynamic binary translator, for example, or might be a system call interposition layer, it's isolated from the application. That's what we use the hypervisor for. Essentially, the hypervisor protects the memory pages of the execution environment from the application and from the entrusted operating system. There was this overshadow thing that came a while back, but now there's all the nesting-based approaches that do that sort of thing. With finer-grained memory, hardware-based memory controls, you can do all of this stuff without nesting or without encrypting pages and so on. But that's the kind of approach we're taking. Obviously, somehow I have to be able to argue to you that a secure execution environment is itself protecting its memory pages from basically influence from the application. So some sort of non-interference argument has to be provable there, which is why it's important to have this stuff be analyzable in a formal fashion. Yes.
Very interesting presentation, but you tackled quite a, like really big topics here.
It was a buffet. Yes.
Yeah. So how do you see, I don't know, the low-hanging fruits here? Like what would be, let's say, the next immediate things which are going to come out of it, and let's say medium and long term?
Well, in research and industry, the next steps are very different. I think in research, in industry? Well, even though I work in industry, I wouldn't be able to tell you because I'm an academic researcher, but I think there's obviously a lot of interest in this, and we've talked to Google a lot, and Google wants to make sure that it compartmentalizes the use of the access to its users' data so that it can repudiate the liability of having data leak. A lot of it is going towards, well, put TPMs in everything and start booting up small kernels of trusted, for some reason, code that isolates data from each other. Again, I don't know how much I want to trust that. Google people are smart. Maybe they'll figure it out, but I would like to see the math, please. So I don't know how the need for math will translate into dollars in industry. I think it's all going to be a matter of what disaster will happen next and how much it will motivate large industrial players in sort of co-tenancy kinds of application hosting to go and build a real solution.
Well, disasters happen all the time, but it's kind of difficult to trace them to this type of solutions, for example, right?
Well, yes, because some of the disasters are misconfiguration kinds of things that sort of fall into what we have assumed is trusted or is all-powerful in the threat model. I think a lot of times what happens is from the vendor's point of view, from the Intel's, I guess, let's say hardware manufacturer's point of view, what happens is a slowly accreted set of features that each one is fairly small. It does very little, but little by little they add an arsenal of protections that might be able to build something like this in 5 years. So Intel this year produced this kind of interesting hardware extension that allows something like the antivirus software for McAfee that lives in kernel mode to be protected from kernel mode malware. It involves some kind of weird memory management stuff that's happening in the hardware. And their goal was to deal with malware, but I can use it, for example, to isolate an application, an execution environment, and an untrusted operating system. So I think in industry, what will probably happen is that these things that have a dollar amount associated with them and therefore can be sold can be repurposed to do something stronger and more, I don't know, world-changing in the long run. I think Intel is definitely planning a long stream of new features that future processors will have to come closer to protecting privacy, closer to protecting trustworthiness of execution in the processor in the future. But unfortunately, it's market-oriented. It goes backwards from what the market desires, which means we need good disasters that will make the market desire the stuff that we have.
Well, I hope you're not going to be creating disasters. Some of these security people have a tendency to want their job so badly that they play both sides of the fence. But in any case,